All right, so we're going to be talking about generators. And as we just saw, here's the big idea. A generator is a motor in reverse. That's it. Generator is a motor in reverse. And to get to our equation for a generator, what we're going to do is to begin with the wire loop, but this time I am not going to power the wire. Instead, I'm going to use the wire to get power from it. We're going to have the wire loop in a magnetic field, and we are going to turn that wire loop. Now, what I found in the other class is the easiest way to do this derivation is calculus. So I'm going to do a little bit of calculus. If you know calculus, you're going to go, uh-huh. And if you don't know calculus, you're going to go, huh. But then we'll just say, here's our result. We know that the amount of EMF generated as we rotate this wire loop is going to be equal to negative of change in phi over change in t, right? And we also previously found that no matter how this loop was oriented, the amount of flux that is going through that is going to be equal to B times A times the cosine of the angle between the area vector and the magnetic field. So that currently, the way, no pun intended, the way that I have this oriented, the area vector is coming perpendicularly out of the board, right? And so the angle between that and the field is 90 degrees, cosine 90 degrees is 0, so we're experiencing no flux right now through this. When I change this 90 degrees, we're going to go to flux max, which is B times A, and then when I change it another 90 degrees, 0, and then negative. All right. So there it is. Let's assume that we are rotating at a constant rate of speed, a constant angular speed. Constant omega. So that I can write that theta, the angle that we have, is going to be equal to omega times time theta is equal to omega times time for any time t. Stop and think about that for a minute, because that's the key part of this reasoning right here. If I have a constant rotational speed like this, then my area vector, which is pointing out of this thing, is going to be rotating around, and it's going to have an angle that is omega times time. Maybe plus a constant depending upon where I start, but if I just make the starting point 0, it's going to go negative. So that I can substitute right here and say that flux is equal to B times A times the cosine of omega t as we are rotating around. Does that make sense to everybody so far? There's no calculus yet. There's about it.
But we don't know how.
Yes, but many of us do. And now I'm about to do the big reveal. This will come as no surprise to you calculus students. And here it is. And that is the EMF is really just the opposite of the derivative of flux with respect to time. And if I now take the derivative of this with respect to time, then I get a fairly simple expression, which is that the B and the A are constant, and the derivative of cosine, as you know, is negative sine times the derivative of the inside, which is just omega. So that when the dust settles, what I get is this expression.
Your fault.
What I get is this expression.
No, I'm sorry.
Okay.
Dented the computer when you pushed me.
Dented the computer.
Apparently.
I know, it's just like one of the little corners. She bumped into the wall.
Well, after he rudely bumped me into the wall.
Okay, well, I'm not sure that we need all this on a recording, so Thanks.
You're welcome.
So that we have, what we have here is a very interesting expression that all of you non-calculus students can tune back into, and that is that the EMF generated by our generator is equal to B times A times omega, the rate of rotation, and sine omega t. Two things to notice about this. First thing to notice is that the faster I spin my generator, the more EMF I generate. Faster I spin the generator, the more EMF I generate. And that's an important thing. The second thing is that the EMF that is output is not constant over time, but is going to be sinusoidal. In other words, the graph of EMF versus time is going to look like this. Let me make this larger so we can see it. It's going to be sinusoidal, and it's going to have a period of 2 pi over omega, because it's sine omega t. And it's going to have an amplitude of BA omega, just like that. We call a sinusoidally varying current like this alternating current. And this is what comes out of the walls, and now you can see why. It's really easy to generate alternating current. All you have to do is have some heat source or something else that's going to turn a turbine. And that turbine can turn then a wire loop or many wire loops inside of a magnetic field. And as it does so, it now is going to generate current sitting into your house. Ta-da! That's all the world of power supplies. Which is pretty cool. Let's see here. Are there other things that I need to say? Not at this time. This is really what I had for you guys today.
It's really cool.
Yeah.
I was just thinking, so you're saying, for